series. This is a series executed by ThinkJ Energy and Energy. And once again, I am Carlo Cariaga, Editor-in-Chief of ThinkJ Energy. Our topic for today's webinar is geothermal cooling. As counterintuitive as that may sound, geothermal can actually be used for cooling. So, to discuss this concept and this technology further, we have Ammar Alali, CEO of Strataphy. He will be presenting the company's Prime Loop technology, which is a patent-pending subsurface geothermal cooling system that replaces or supplements conventional cooling infrastructure. This technology has now been deployed across multiple sites across Saudi Arabia and is the first commercially operating geothermal cooling solution in the Middle East and North Africa region. This session will cover the fundamentals of the technology, the use cases in data centers, and pathways to commercialization. Dr. Ammar Alali is the CEO and co-founder of Strataphy. He holds a PhD in geophysics from MIT and a BS from the University of Houston, and he has spent over a decade at Saudi Aramco's XPEC Advanced Research Center in Subsurface Systems (R&D). He is also a member of the Saudi Leader Society and an ISADE Executive Leadership alumnus. For everyone in the audience, if you have any questions, you can just send them in via the questions tab. That you should see them in your webinar panel somewhere, and we'll get to those questions after Ammar's presentation. And with that, Ammar, welcome, and the floor is yours.
Thank you so much. Hi, everyone. Good afternoon or good morning, depending on where you are. As in the introduction, today's conversation will be about geothermal cooling with a specific focus of identifying a market which we believe could be a unique opportunity for geothermal, a direct application, either heating or cooling, but mainly for data centers, it's going to be cooling, except with ambient heating if needed in certain location. And I think it will be a massive opportunity that the geothermal industry needs to activate, tap into, utilize, expand on, go very big on, just because the numbers I'll walk you on are very appealing. So the conversation today, as you're going to see it, is one really driven by the use case and identifying this gap in the market and how sizable it is, what's the potential impact for it, how does all these numbers do, what is the current cooling solution utilized today. I understand a lot of the people in the audience do have a geothermal background. So we're going to cover that in the second section of the presentation. I'll keep it high level for two reasons. One, a lot of the fundamentals are well established. Two, the kind of the nuts and bolts of the technology we like to reserve close to us. So you're going to see some slides with some information, not necessarily as revealing, but highlighting this. I want this to be as engaging, especially after I finish the presentation. Feel free to ask any questions. I have some materials that I'm not going to go through in the slides in the presentation, but I could roll back to and bring it and present it as needed if there are certain question takes one direction or another. Great, let's get started. So at Strataphy, we are laser focused on one type of direct use application, which is cooling, and specifically the cooling demand driven by data centers or cooling any digital infrastructure. And this case is extremely appealing for us because one, the growth of where it is today and where it's going to be in the next year, 3 years, 5 years is significantly higher than any other application. Specifically, frankly, if you look at any application for geothermal, the growth anticipated as a percentage year-over-year growth of an application for cooling is the biggest out there. Two, the load it requires present a current challenge for other solution that we think geothermal is going to be appealing. So the loads this infrastructure requires seem to be constant 24/7 all year round. It also tends to be very driven by any cost savings. So minor cost savings, minor optimization could translate to bigger numbers, bigger economical value, aka potentially faster and better adoption for geothermal. Now, why is this the case? Because data center as an infrastructure is growing at an unprecedented rate, starting from the global picture. Current data center, now a lot of these numbers could be optimized, could be corrected, but as we know it, I think, let me look at the source here for the Goldman Sachs and McKinsey studies. I think that was based on 2025 numbers. or mid 2024 number, so not very long time ago, the current size of that infrastructure is roughly 55 gigawatt. Now, this gigawatt electricity, and we typically assume the thermal load is 1-to-1. Now, it could be slightly higher, actually, the thermal base, but assume let's run with 1-to-1 conversion between power demand and thermal demand. Now, this number needs to grow by roughly 3.7 times by 2030. That's in a span, if we assume this number is end of 2024, that's in a span of 5 to 6 years. So we need to multiply all the current facility ever built in all countries globally by that multiplier of 3.7 to get to this number. Now, if we zoom in the Middle East, where we are laser focused today, that number is 15 to 30 times multiplier. Current infrastructure sits around 0.75 to 1 gigawatt, and each countries in that region, specifically there's 3 countries, Saudi Arabia, Emirates, and and I think Turkey is pushing a lot toward data center infrastructure. The size needs to be multiplied by 15 to 30x multiplier to jump to 15 to 30 gigawatts. Again, this is the driver for all of today's conversation, which is the growth, the market growth, the application for our technology. Now, why does this matter? How does those numbers in infrastructure built to be done, of any relevant to you? Today, the current consumption, or what they call the rack density per AI, or could be frankly mining operation, or an usual hyperscaler data centers, normal compute power using CPU, not GPU, you could focus on how much energy a rack is consumed. That could translate to the density. So how much energy you're utilizing in certain meter by 1 meter, right? This number is actually also growing. So the growth in this space is they used to have 1 rack, so the same footprint. It's roughly 5 kilowatt. We started to see 25 kilowatt. Earlier last year, we started to see 100 kilowatt. Today, if you talk to data center construction companies and design companies, they're looking at 250 kilowatt. There is NVIDIA talking about potential rack that could sustain 1 megawatt. So that's a significant 2 magnitude higher growth in energy for the same footprint for the rack and the data center. Now, the issue that comes with that, you have the technology advancement happening on these GPUs or CPUs, depends on what you're using, a different type of GPUs. Let's run with the GPU 300. So you have significant advancement happening with the specific chips. So that allows it to consume more energy. That also allows it to make higher revenue by producing higher tokens. But the infrastructure required for electricity to meet that demand and cooling to dissipate the heat generated by that rack is not improving in a similar, let's say, rate, right? The energy production, you could facilitate that by cables. So you could have the source of energy coming from any source, could be geothermal for power production or any other source for power production. And it doesn't have to be on site to be a large solar panels or a large geothermal plant. With cooling, you need to have it on site. So that represents the challenge. So the challenge is these racks are producing significantly higher thermal heat, right? This heat needs to be dissipated because you can't the heat concentrate and build up. Now you have different temperatures that you want to target by the cooling, but the common theme, this heat needs to go somewhere. Current cooling solutions are not reducing in size by 1 magnitude or 2 magnitude. In fact, the changes or adoption of technology advancement with cooling solution has been extremely slow in the past 20, 30 years. We'll walk you through the options that they use today. So that's where the significant bottlenecks comes in. I could have the same footprint of a data center that could consume 1 magnitude higher, potentially 2 magnitude higher in the span of 4 to 5 years, but the infrastructure for everything else is not getting as smaller, and it seems like the cooling is the major bottlenecks because it needs to be done on premise. Now, if you don't dissipate this heat, you have the problem builds up. So as we've mentioned, compute power, whenever you hear about the data center size, you could assume a similar volume in thermal unit needs to be dissipated. So 100 megawatt electricity size data center typically require 100 megawatt thermal cooling system. Um, if you don't meet that demand on a similar size, you have a buildup of heat, thermal energy, that typically results in performance limitation, failure on equipment, efficiency reduction, and all of this could translate to reduced revenue or outcome or token produced by this data infrastructure, especially during certain hours of the day when it's relatively hotter outside, right? So how do they mitigate this issue today? Today, the cooling solution for a lot of these, well, virtually all data centers really trickles down to three types, and the first type have different variation of it. So the first one is air-based cooling. Air-based cooling could be an air chiller, it could be a package unit, it could be a dry cooler. A dry cooler does not have mechanical cooling parts. So think about the cooling system. What does your HVAC typically include? Include a compressor, that compressor refrigerant, include a condenser, that this compressor refrigerant that is 70 degrees Celsius or 80 degrees Celsius or 60 degrees Celsius, depending on where you are, goes to a condenser unit. This condenser unit, all it has is heat rejection. So it has these fans, it blows into this compressed refrigerant. That heat dissipates from this compressed refrigerant because the compressed refrigerant is actually warmer than the temperature outside. So you're technically taking heat into the ambient condition. Then it goes to an expansion valve and release the pressure. So the refrigerant temperature drops significantly as a function of releasing the pressure and as a function of dissipating some heat when it was under pressure. So you're pretty much using a leverage in your heat rejection. Then it goes back to whatever you're trying to cool. A dry cooler does not have the compressor or the expansion valves. It just has the condenser. And a dry cooler is typically used if the temperature outside is really cooler than what your liquid cooling or whatever chilled water network is. So you could avoid using a compressor, and the compressor typically uses most of the electricity and avoids the expansion valves as well. But ultimately, that's what's called air cooling. The name comes from the fact that you're taking the heat and rejecting it into the air directly without a liquid medium in between. This method uses a lot of electricity, but does not use any water, which is good depending on where you are. If you don't have access to fresh water, if you don't have access to any water, you typically go with this method or the variation of it for dry cooler if you live in a colder climate. The second method is the chilled water with cooling tower. This is what typically referred to as district cooling. Same mechanics, compression, expansion valves, but the condenser or the heat rejection function utilize a heat exchanger between, let's call it the hot loop and the cold loop. So the cold loop is where you're taking the heat to get it cooler. That's the condenser. This condenser loop takes it to something called a cooling tower that looks something like this. This cooling tower is using evaporation as a method to dissipate heat. So you're literally evaporating the water to make it, well, you're evaporating part of the water to make the water return cooler. Then it goes back to the condenser, and that's how you reject heat from your cooling cycle. This system is way more efficient from electricity perspective, so consume less electricity for the same cooling load, but it also consume water. So you constantly need to bring fresh water or new fresh water to fill up the cycle and continue the cycle. So penalty of it is water utilization. The good side of it is electricity efficiency. The common method that we hear everywhere about a data center is liquid cooling. And now, again, there's different variation of liquid cooling. Let's go direct to chip to immersion cooling. So you're using literally some sort of dielectric fluid, typically in oil, um, to immerse these chips, GPUs, typically in it to take the heat faster. So your heat transfer from the hardware that you're trying to cool, which is the chips, to the fluid that you want to take the heat is direct, it's more efficient. So you're improving the efficiency significantly in this piece, but then you have some sort of heat exchanger. This heat exchanger between whatever fluid you use in immersion cooling and you typically water on the other side. Then it goes to heat rejection function. And that could be the dry cooler, which is literally just a fan blowing in water to dissipate the heat, or that could be some sort of evaporative-based cooling. Now, the last method, you're really not changing any fundamentals. You're changing how you extract the heat from the place you're trying to cool, which is very, very good and very smart. We can't do that to human. I can't cool a human by putting it into a bag of water and telling them, go live your life. I can't do that to machines, CPUs, hardware. However, none of them is, in our opinion, is significantly better than the other ones, because if you added up your total cost of ownership from a capex and an opex and economics for cooling could be done significantly better. So there's one metrics we typically use to identify what is this better? Where do you want to get to? What is this economics of scale that, or economics of cooling that you want to follow at a data center level that determines which one you're doing. So one, high electricity, one, electricity and water, one is just changing limit to do it. All of these metrics, or typically the metrics are used in data center to see how efficient overall your data center, but mainly how efficient your cooling is called the PUE, the power usage effectiveness. And what it is, it looks at your total facility power consumption divided by your money making. So your money making is your IT power. So how much of that electricity going to your IT power, how much of that electricity is going for the whole data center demand? This, this number in perfect situation when you have no losses, nothing at all, it's 1. That means all of your electricity consumption goes to the GPUs, and this GPU produce the tokens that gives you the money, or ultimately this is how you make money. The theoretical limits is closer to 1.05, 1.1 for mechanical PUE, because you always have losses in the cables and the connection. Best practice is getting that number to 1.2. Now, the global average used to be 1.4. Now we're seeing the global average lower. It's closer to 1.3 or 0.25. In hotter climate, though, because the method of cooling tends to be active mechanic-based, compression-based cooling systems, or dry, or in this case, cooling towers with water, you either have a high PUE that's closer to 1.45 to 1.5, or you have high WUE, which is the water usage effectiveness. Now, WUE, perfect situation is 0. That means you're not consuming any water. Now, in situation where some water is going to the cooling and none of the water is going to the IT, this number becomes big, and you want to avoid that. Now, with district cooling, you have a significantly higher WUE. With air cooling, since you could achieve 0 WUE, right? Now, let's go back to the PUE. So higher is bad, 1 is perfect. Where is this bad above 1 number coming from? Majority of it goes to cooling. So when you look at this PUE higher than the 1, you have some facility loads, conversion, distribution losses that typically is higher than this. It could be 0.05 to all the way to 0.1, but the remaining is cooling. The light that you have in the system, everything you have in the system is very minimal. Cooling comes at a significant cost. This cost could be represented by how much money you're spending every year in electricity consumption that you don't make money out of it. And this is typically when we see an opportunity and when we see a challenge, that's where the opportunity lies. When you have a problem, that is where potential opportunity comes from, where, hey, if I make this better, there's how much I'm saving. So we're going to look at that. What if we're able to reduce 1.04, 1.05 to significantly lower numbers? Now, for a typical size data center of 300 megawatt, your grid connection needs to meet a potential demand of 450. And that's what's called PUE peak. So at peak cooling demand, what does your PUE looks like? Even if you only get to that peak demand 1 month of the year, you still need to have infrastructure to meet that maximum peak demand at any given point of the year. So grid connection needs to be 450. Now, if you assume that PUE average is 1.5, and you're able to reduce that average PUE to 1.02, that's a significant meaningful reduction that could be represented in lower facility power requirement by 90 megawatt, That also could be represented financially by reduction of operational expenses. And here we're assuming roughly 4 cents per kilowatt hour. So usually they get subsidized prices because they either generate power or tap into power resources that's close by or subsidized by a different government. If we go with that number, you're looking at roughly $67 million a year that you could theoretically achieve by reducing your PE from 0.5 to 1.2. Now, as you scale this number, obviously there is a linear relationship, and here we're making a lot of assumption. We're assuming the electricity prices doesn't change, there is no inflation, your utilization is still the same, and your load is fixed, which it tends to be the case, that your load in data center, because the source of thermal load is internal, it's not external, so it tends to have the same cooling load all year round, every day of the year. And in that case, you could be looking at a significant cost saving potential. Now, those numbers, a lot of government have set numbers that they want to hit of AI, specific AI data center infrastructure that they want to meet by 2030. Some countries set 3 gigawatts, some other countries set 6 gigawatts, some other countries more. But here, for the sake of example, let's go with the 6 gigawatt. That's a potential, significant potential of cost saving of 1.6 billion a year. Now, comes the geothermal element. All of these solutions, what makes them, in my opinion, not ideal, because they tend to be extremely reliable on what the temperature and condition of outside are. So if the temperature outside is 35 degrees Celsius, you're going to give different efficiency than if it is 45 or 55 degrees, especially in the Middle East, versus if it's 20 degrees there. So you're always vulnerable to what the condition outside, what's the humidity, especially for cooling towers, what's the temperature for air cooling, and so on and so forth. Prime loop, the main driving difference, does, like any other geothermal solution, it taps into the ground. Now, typically, whenever you have, and this is kind of a simple schematic of what it is, typically, whenever we think about geothermal, the prime loop system, or typically any geothermal system, has the advantage of tapping into cooler temperature. Now, these temperatures are going to vary. Some location, you're going to have a subsurface temperature as low as 15, 16 degrees. And to our surprise, there is certain location in Saudi, even though it's a very hot country, where the subsurface temperature or specific depth could be 16 to 17 degrees Celsius. So that gives you a massive advantage right off the bat. Second thing, those systems are completely water-to-water exchange. So you're constantly using an exchange through water-to-water. You're not using any air medium. All of the system I talked before, you're at a certain point, you have a fluid exchanging heat with air. That's less efficient. The distribution could still be the same. This technology doesn't change anything about distribution. That's what liquid cooling does. And the reliability could be also the same. So typically, the reliability for geothermal system arguably are higher, but let's say they're the same. Electricity supply is a key. Most data centers are away from the cities, and whenever they're built, they need to have their own substation. Substation and grid connection are extremely expensive. So any improvement on the total load, peak load at any point of the year, reduce your initial investment in substation, ultimately reduce your capex to build the facility. The golden metrics we like to at least talk about all the time is the coefficient performance, which is what is the electricity consumption for whatever load you have in thermal exchange that you need. At normal air chillers, again for air chillers system, the COP could be 2.7 to 3.1. Dry coolers, because they don't have compression, they could shoot up to 15, 16, 17. Our system, if they need compression, are connected to water-cooled system, that could be 6.5 to 8. Without it, it could be shoot up significantly higher. The life cycle is also a big difference. So again, especially if you're under the sun and with dust, this life cycle could be significantly lower for air chillers versus our system. They live longer. Now, what's unique about what we do? We have we believe we have 3 pillars that makes us uniquely positioned to do what we do. One is we're always driven by the strata, the stratigraphy under the ground. Where is the right lithology and what is the right temperature for the perfect lithology? So we typically look at the presence or absence of water, temperature of that body, thermal conductivity, and all these usual metrics. And the design comes from down onward. Then based on that, we start the design criteria. What's the load? What is the right material that we need to use in the system? You can't have one material used all the time. What is the right pump that you need to use in your system? What's the right control metrics? And we're building in a significant many years of experience with these systems. In general, geothermal, but specifically the systems as well. Last thing is the patents, and I keep the patents the last thing because I think having patents is great. It's not always the winning card. You need generally patents are very general. Whenever our patents are published, everybody will be able to see it. So you want to keep them as generic as possible. So there isn't much uniqueness to them. You need to be able to actually execute and know where to execute and how to execute. Now, we kind of did a quick walk through all of this. Now let's talk commercial stuff. Market sizing, whenever you look at the global market, it's significantly bigger. And one thing I want to highlight is like when you look at a global scale, a drop in the PUE or 0.1 drop in the PUE could result in significant money or cost saving to the client. That we're talking 10 billion more just for one drop or 0.1 in the PUE. So anything that moves the needle, because you have concentrated demand, that any improvement on these concentrated demand result in a significant value, larger impact. And that's why I'm extremely passionate about this application. Now, also talking about business and commercial, we think there is a lot of pain point associated with adoption of geothermal. And that's something I've talked before on other podcasts. We tend to mitigate that issue by reducing the adoption hurdle or adoption friction. We think geothermal typically tends to scare people away because it's a new technology, especially in power production. It doesn't have the best capex economics from day one. The payback could be high, et cetera, et cetera. Now, this doesn't apply for cooling. We think cooling payback period is much significantly shorter, is very attractive. But how do you mitigate that adoption friction? The way we like to do it is we do the A to Z. So we provide this as a service. We typically, our client pay us a one-time integration. Then we do the site survey, the design, the procurement, the installation, the commissioning, and the operation and maintenance for 20, 30 years. In return, our client pays a subscription. So we make this as much as possible of hands-free from the client perspective service that they get. Then we charge them as a function of consumption and hitting targets. So how much you use the system and what is the cost saving against what we promise you you're going to get, you got. And this is how much we charge you every month. Quick case study. We've looked at a case study. We can't specifically talk about where it is, but it was roughly 5 megawatt. It was using dry coolers, so no compression. The temperature, whenever ambient temperature exceeds 33 degrees, the dry coolers don't give you the same efficiency and don't give you the same performance. You're ultimately resulting in roughly 15 COP, or COP for that specific site was roughly 15. When you multiply, and this site was operating 24/7, I think 99.99% of the time at the same load. It was roughly 4 cents per kilowatt tariffs used. So roughly we're spending $100,000 on cooling costs, mainly electricity for cooling system. With our system, we could reduce that cost significantly, roughly by 54%, driven by less electricity consumption for our system. And that translates to roughly $55,000 a year saving. This is a quick skim of the actual schematics. Now, a lot of data centers, especially the new ones, the GPU 200, GPU 300, are going to require higher temperature loops, which could be, again, very great for geothermal to come in and really disrupt the space. Lastly, who are our partners? We're proud to have Baker Hughes providing us with equipment. We're also proud to have Saudi Tabreed. We signed an exclusive agreement to go after data centers with them. They're a large district cooling company, and they partner with us in the execution of data centers. Thank you for tuning in. Love to answer any question. I guess back to you, Carlo.
Okay, my audio is back. My camera will be back in a bit, but is my audio okay, Ammar?
Yes, I can
Yeah,
hear
okay
you.
then. Okay, got it. Thank you for that presentation. That was a very good, very quick also summary of the opportunities for geothermal and data cooling. Of course, there's a commercial opportunity, but also it's very good to know that it also helps reduce the environmental impacts of data centers and also reduce, I guess, the surface footprint of data centers, which definitely helps with social acceptance. Okay, so for everyone in the audience, just feel free to send in your questions. We'll get to them in a bit. We have 20 minutes. Uh, okay, well, let's start with one of your, say, the foundations of your concept is selecting the right strata for 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 cooling, for providing cooling, or as a heat sink for the cooling system.
Yes.
Um, do you find that there are different different geologies perform differently when it comes to cooling? And is the system customizable based on these different geologies? Like, do you have to customize, say, the downhole system, or do you have to drill more boreholes or more prime loops, depending on the settings, depending on the geology?
Absolutely, yes. So you need to do a couple of things that we look into for the strata. Typically, we look at what is the thermal conductivity on this layer, what is the equilibrium temperature of this layer whenever you finish drilling, and if the temperature settles after X amount of weeks. What is that initial temperature of the strata? And you want to get a good profile for multiple layers to find the right layer. So intuitively, you think the temperature will normally just go higher with depth. But again, because of the sun radiation in the first couple of layers, you actually find a sweet spot that is not the first layer um, in the first, let's say, 300 meters. So you need to find what is the exact lithology within that depth to meet your best thermal conductivity, presence of water or lack of water, porosity, permeability, chargeability. And that's all these normal tests that you do with thermal response test, open loop geothermal test, which doesn't mean the geothermal system is going to be open loop, but you need to flow that reservoir, re-inject it again. These are very common standard people use in any geothermal heating and cooling application. All of these things are going to give you some parameters, then you flush them through your analysis and say, yes, I could do the system with this design of my downhole system with this number. Also, what we typically do, we do thermal loading. So we look at the thermal impact. Now, whenever you have a cooling system today in your house or your apartment, you don't think a lot of the thermal buildup in your cooling system because it's set up at the roof, it rejects heat at the roof, it dissipates on ambient condition. Um, when you have large system, it becomes a problem even about in the roof of your house. When your cooling system rejecting heat, and that becomes the inlet in the other cooling unit, that becomes an issue for your cooling system. The same applies under the ground, and we need to model that over a long period of time. If my system run with this load profile, is it fixed? Does it change month to month? What is the thermal buildup under the ground? How is it going to impact my system performance? Then that's going to determine the design of the downhole system, the depth, how many wells you need, what's the horizontal distribution of your wells. All of these are going to become an input to how you design the system. So honestly, you start with this to optimize the second layer. So you start with the strata intelligence or the approach to finding the right stratigraphy to be able to optimize the system design.
Okay, then we have a lot of questions coming in. For our audience, like I would like you to understand as well that, as Ammar said, this is patent pending technology. So there are definitely some details or some questions in here that probably won't be answered completely, but we can try to mention them anyway. So there are
Yes.
questions here on how deep the wells will be, and also what kind of fluid are you using in the downhole system.
Yeah, I mean, also a really great question, and I'm glad you've mentioned that because I specifically told you that I expected them. Unfortunately, we can't reveal a lot of the things that we're doing. We just the very protective answer, and as you can see, I really didn't show even what's under the ground. Is we typically have a system that is installed this college within the first 500 meter, so they're not very deep. Um, everything else would be very hard for us to discuss at this point. But what you see at the service, or what we're focused on for what people sees at the service, is pretty much just the plastic pipes that comes from the ground. Two plastic pipes. One goes hotter, the other one comes back cooler. And from the service from your client and from your perspective, the service, this is actually a closed loop that comes in and out, but downhole it's not.
Okay, then I think that's about all of we can discuss when it comes to those questions.
Yeah.
Okay, here's a very good question. How does the prime loop system adjust to potentially fluctuating cooling demand of data centers?
So good and bad thing. Data centers don't have fluctuation mode. They tend to be pretty stable. Now, it doesn't mean it's the same value. Yeah, typically, whenever you think from the construction point of view for data centers, a data center is built at a certain capacity, but you don't start day one with this full capacity. Let's say data center built by 20 megawatt. You don't have 20 megawatt GPUs operational from day one. So you're going to start with 2, 5, 7, whatever, 10. Then you build it up. But whenever you have these off-taker agreement, they tend to be a long period of time off-taker agreement. And this is what they call the agreement between the construction company that builds it and the people that are going to buy it, or you buy the token for it, right? And whenever this agreement is set in place and it's operational, that load stays fixed. The, it's counterintuitive because we're used to cooling demand for buildings, for commercial building, industrial building, your house, and residential, you name it. And those tends to be a function of what is the thermal energy inside, which is influenced by how hot it is outside. So at night, you have lower thermal load. Later in the day, you could potentially have lower. Sorry, at night you have lower, and during the day it becomes hotter. Data centers have the thermal load inside. So inside of the data center, the thermal load is high. Um, so it doesn't really fluctuate. Now, if it does fluctuate because they lower the need for it, they have what's called an allocation but not utilized allocation. That's not a bad thing. That's actually a good thing. It's a good thing for all conventional. So again, whenever you think of all geothermal heating or heating cooling application that exists today, it tends to be a good thing. They call that a recharge period. So you are allowing your system to recharge, and you're allowing your thermal energy dissipating near the ground to build up, actually. So it's actually a good thing, not a bad thing.
Okay, well, your answer actually sets up the next question quite well. I know we talked about data centers as a huge market for geothermal cooling, but is space cooling still a viable market for your technology, or is this is this still too small for you, even in, let's say, a Gulf country, a Gulf region country?
Space cooling mean like residential or commercial?
Yeah, I mean, yeah, space cooling for
So
residential or industrial.
yeah, okay, those are two big. So residential is no. I don't think the economics for our technology will work for residential now. If you have residential, you're better off doing what everybody else is doing today, which is closed loop heat pump approach. That could work for cooling and for heating if you need it. Or typically in the Gulf countries, the load per house is much bigger. We're talking per house is 80 to 150 kilowatt thermal load, maybe even higher. Um, versus if you have that load in Europe, it's a fraction of that, it's a third of that. Um, but nonetheless, the economics do not work for residential. Um, they could work for commercial, but it needs to also be a large commercial. So you can't have one store and you've got like, can all this work? Which really kind of hammers the point of our business model that I talked a lot about in previous podcasts and panels and here today. And for this business model to work, we need a large system. So, and large typically means large commercial, industrial applications.
Could it work for, say, a theoretical city or town which has a cooling network, a district cooling network? Would that be
So
large enough?
yes, and I know that was what happened to the light here. Hold on, let me see where it went. I know there's a lot of application. Here we go. It's back. I know there's a lot of application in Europe where they do large network for cities or a whole district, literally district geothermal heating and cooling. Um, we haven't come through that application. I think it could work, and I think it does work. Um, and this is when it becomes you're really driven by optimization. So what is the maximum load you have at any point of the year? Because you have a lot of house, a commercial application on a large district network. Not all of them going to be on a full capacity at the same time. So you get a lot of optimization there, and your system could perform very well. I think in this application, actually, the application would work very good. We haven't looked at it for multiple reasons. One, distribution from one centralized system for heating and cooling to multiple users, that could be it residential or commercial, requires certain permits to be effective and working, and your ability to go and charge multiple clients. Two, whenever you need to do that, usually it's a municipality-driven effort, because you're typically going to cross streets, you're going to cross municipality infrastructure, you need to literally make holes or connection or piping in these things. So practically, it could work, but it could also be challenging at the same time. But I think economically it could work, technically it could work. I know Geneva is soon enough commissioning a large district cooling. Munich has the largest, I think, district cooling or municipality-driven adoption of geothermal for heating and cooling in Munich. Frankly, I was supposed to visit it this week, but it didn't pan out. I plan to visit it at some point this year. One of our team members, Ammar Alali, has visited the facility in Geneva. I've seen it. So it's intriguing. It could work. I think the economics would also work there.
Okay then. My question has two parts. My next question has two parts. So the first is for as you mentioned, an average data center with a demand of 300 megawatts. How many prime loop systems will that need? And also the second question is for if there's, say, a project design team that wants to implement a data center in the future, what are the parameters that they need to tell you? They need to give you so you can design a system for them.
So the first part is very hard to answer because of the second part. So typically, the decision of how many loops or how many prime loop system you need to get to is always going to be driven by what is the cooling load that we're looking at. Is it, as we talked about, is it a fixed load for a data center, which tends to be the case? What is the temperature? And this varies a lot. So when we think about residential and commercial buildings, usually for large commercial and industrial, you have 712 temperature. So 7 Celsius output in your evaporator, the return is 12 degrees Celsius, because typically that tends to be 10 degrees difference between your chilled water and your output air temperatures. And that's where the human like to be in, 17 to 25 degrees Celsius. If you're trying to sleep or if you're trying to work, you're going to sit in between that. Now, if you switch to data center, you're talking about hardware, and they could completely have different temperatures. So we've seen data center design with a temperature requirement 20 degrees Celsius. So data centers require 35. We've all heard, not all, but a lot of us heard NVIDIA CEO Jensen claim that the future of data chips requirement is going to be 40 degrees Celsius or higher. Now, this does not exist for industrial and commercial. You don't have anybody trying to sleep in 40 degrees Celsius in their house. It's very hot, but you have that for your machine. So, and that's a big, significant change. That's almost 20 degrees temperature difference from one data center to another. All of these things are going to be contribute. What's the thermal load? How do you design it? Also, what's the footprint? The one thing I could say that when we started in January 2025, we launched, and we had our first system kind of tested that period of time. We were looking at 200 kilowatt thermal output per prime loop system. Now we're significantly higher. That's all I could say at this point, per prime loop system. So the economics became very, very attractive. Now we had to make significant leaps in how we designed the system. We're able to reduce the number of falls needed by 70, 75%, easy. And that becomes a significant, not necessarily capex, but footprint attractiveness to the client adoption and reduction in lead time. So a lot of clients for data centers, they care about, they're going to give you the parameters. What is the cooling output? What is the required temperature? What's the flow typically required? What is the distribution network that they have on the other side? Design your system based on it. But they also care about how fast you will be able to come to site, install and commission a system. Do you need 6 months? Do you need 1 month? Do you need 3 months? Do you need 12 months? So you could pre-plan everything, like all the hardware and procurement, you could pre-plan it ahead of start date. But the drilling needs to be within the execution period. You can't pre-order a well in the ground and you get it by Amazon. You have to go to the site and actually drill it. So if you're able to reduce that number, and if you're able to really be a game changer of how quickly you could execute these wells and of the smaller number of the wells that you need, then you move the needle with your client and reduce your lead time.
Okay, speaking of pre-planning, what are the surface investigation methods that you need to do before you deploy your prime loop?
So we do the usual, honestly. For us, there is, with the exception of one geophysical survey that we've actually developed in-house, we worked with one institution to design a specific geophysical survey, and that becomes actually one of our unique advantage. We're able to go to one site and get a lot of information from the ground in the same day. So we're even integrated AI in the interpretation. So we're able to take geophysical survey, use AI to interpret the whole data, and gives us the areas of interest. And that's something we didn't talk a lot about in the past. But then after that, you do your usual. So after you drill a well, you could run a thermal response test. That's very standard. Everybody does that in the space in geothermal heating and cooling. Thermal response test, you literally artificially create heat in a fluid, and you see how much heat dissipation happens under the ground. The other test is you do production and ejection test to see how much you could flow out of the water. So after you understand the thermal conductivity, you need to understand your aquifer production, dynamic water level, static water level, porosity and permeability of the formation. Then we also could run logs for a new site, your typical logs that you could run, frankly, for any water well or oil and gas well. We also adapt those. So it also, our unique surveys and the planning comes with this geophysical tool that really allows us to make it a quick decision. Usually we could collect the data and get the result instantly. Do we want to look here, or we don't want to look here? And that's for us, because everything else comes at a massive investment. The minute you need to make a hole and run all these tests, you're really kind of spending a lot of money in it. So we created a tool that allows us to get a yes or no before we start the drilling.
Okay, as you mentioned, you do thermal response tests before you deploy the prime loop. I'm curious what the results of your modeling is, because is there an operational limit to say the degree of heat dissipation that happens in a in a single borehole over 30 years? Do you need a backup prime loop at some point based on your modeling?
So yes, this technology will not and cannot work everywhere, but no technology does. No technology in the energy space works everywhere. So what we're seeing is certain location under certain condition parameter, the performance either decline as an output, or the efficiency or your COP is in that case also declining as a result of certain parameters and values. And that also trickles down to how long I could run the system under a variable load profile or a fixed load profile. At which point do I create so much thermal load in my location that I cannot run it? After how many years? After what condition do I get to that point? And there's always any commercial industrial client is going to require backup. And then of course, the prime loop backup, holes under the ground backup. Then you have the question of what is the rotation you need to adapt. Just because you have a backup, and again, what I'm saying is very common in any cooling system, even air chillers, you could have backup or redundancy, and you could actually utilize your redundancy whenever you're running maintenance in your MERS system. So you could do the same thing for a geothermal system, and that's could be prime loop, it could be pump redundancy, it could be chillers redundancy. And typically there is a specific standard that we follow. For data centers, there is organization that actually set the standards, and we actually even had, I think one of the team members attending this panel had to attend a course recently with one of these organizations to be able to deliver systems that meet these standards, including the point if you mentioned how many backup system do you need, what's the redundancy that you need as a function of the thermal load and efficiency reduction over time, if any.
Okay, yeah, well, that makes sense. I mean, before I move on to my last question, I'm curious about the cooling as a service model. So, is this something that was driven by the market? Do you find that more clients prefer this, or is this something you decided on as a company?
Um, it's both, really. I mean, honestly, we started with a spectrum of option. Hey, do you want this to be an EPC? Like I give you a product that you pay me and I come install it and commission it for you. So I engineer, procure, and commission, and I get paid a CapEx line item and I go home. And we think that approach has many bad elements to it. It slows down adoption. It puts some risk on the client. Why do I need to pay for this? This is a new technology, which it is. The whole system is new. I don't have data for many years to show you my system have worked for 20 years. Come buy it, right? It's a new technology or a new design. So for me to get you to a buy in, I say like, listen, don't pay anything. I'm gonna adapt it, the whole system from design, procurement, installation, and commissioning. All you have to do is pay me once you see some results. The second thing is purely commercial. So one is adoption. The second thing is money. So if our technology works, which we know it does, and if it provides cost saving as promised, which we think it will, and it has, we have enough data now. One of the system we have data on more than 15 months, 16 months at this point. We could then actually retain more of the value we create to you. So if I am a CapEx line item, the best I could get is a margin on the CapEx of my cost, and I add a margin, what I see what the market prices, and I go home. Versus if we make this like a PPA, but for cooling, so it's an energy purchase agreement virtually, I constantly have to maintain and make sure the system works and works very efficiently, but I also make money constantly. So those more attractive for us as a company as well.
Okay, then we still have a couple of questions, but I think we have to wrap this up. So, my last question is this: with whatever you can divulge to us, what can we look forward to with Strataphy? What are you working on for the next few months or years?
Um, a lot. There's a specific project that we are extremely excited about. We can't reveal it obviously just yet until it's a done deal and we start the work. But hopefully that would be our biggest. It's with a client for a data center, and it's a very attractive project from all elements that we've looked at. So purely kind of execution. The second thing is market penetration. So we operate in Saudi, Emirates, soon enough Oman. The last jurisdiction we're looking at right now is the US. I don't know if you follow us on LinkedIn. We talked about a potential client in the US. Hopefully, we're also going to make new announcement in the US. So market penetration and execution of project. We don't reveal much, honestly, about product development or technology. We like to retain that very close to our chest. So a lot of the new things that we hopefully will come about very soon in the next couple of months will be in these categories: project executed and market penetration that we came into.
Okay, perfect. We are all looking forward to more from Strataphy for the coming years. Thank you, Ammar. Thank you for the presentation. Thank you for sharing your insights and your progress. Thank you to everyone in the audience who participated and those who submitted questions. I think we had a very good discussion, actually. And so,
Perfect.
thank you, Ammar, and goodbye. Goodbye to everyone. Have a good weekend.
Thank you, Farlo. Thank you, everyone.